this is lecture number 3 of electrical drives. This lecture is starting with the loads with translational motion. Translational motion. That is, linear velocity is associated. Then first, if I draw the block diagram, we are having a motor which is directly coupled with a load torque, that is load having torque is TL0. Okay. Now, obviously, if the motor is rotated in this direction, this is the direction of omega m, the load torque is the opposite direction from the omega. Okay. Next, the rotational to linear motion transmission. Which is driving a load having mass m1 and a force is applied to this body F1. Say the velocity of this body is downward v1. Okay. This is the overall block diagram of the loads with the translational motion. Now, if I calculate the kinetic energy of the different parts, then say equivalent inertia of this motor load arrangement is J0. Okay. Then half J omega m square. J is the kinetic energy referred to the motor shaft. Total kinetic energy, equivalent kinetic energy referred to the motor shaft. That is half J0 omega m square. Kinetic energy of the different parts, the total kinetic energy of the different parts will be the same as the motor will face, plus half mv square m1 v1 square. Okay, that becomes J will be J0 plus m1 v1 by omega m whole square. Okay, this is the equivalent kinetic energy referred to the motor shaft. This is J is the equivalent kinetic energy I'm sorry, not equivalent kinetic energy. There is the equivalent inertia. Equivalent inertia. Referred to the motor shaft. Okay. Next, if I calculate the torque, then obviously the power of associated with the different parts will be the same. The torque, load torque faced by the motor, that is the TL omega m, becomes TL is the nothing but the force multiplied by the radius. Then TL omega m will be TL0 omega m plus F1 V1. F1 V1 is the power associated with this system, with this linear system. Power is the F1 V1, and if I consider the transmission efficiency, then it reflects to the motor shaft by dividing eta 1, where eta 1 is the efficiency of the rotational to linear motion converter. Okay, and power associated with this body, power is the F1 V1. Okay, that is the force multiplied by the velocity. In case of rotational system, torque multiplied by the angular velocity is the power. Then equivalent torque becomes TL0 plus F1 by eta 1 V1 by omega n. Okay. Next, if I consider there are number of loads is connected to the motor shaft by different gear arrangement or different linear to rotational to linear motion converter, then for m number of loads, if I consider m number of loads, then equivalent inertia J becomes, what is that? J0 plus m1 by m1 into v1 by omega m square. Okay. J0 plus J1 sorry, this becomes m1, not J1. This is m1 v1 by omega m square plus m2 v2 by omega m square plus m n vn by omega m square. Okay, and the equivalent torque referred to the motor shaft becomes TL equals to TL0 plus F1 by eta 1 V1 by omega m plus F2 by eta 2 V2 by omega m plus Fm by eta m Vm by omega m. Okay, this all about the equivalent inertia and equivalent torque referred to the motor shaft for the translational motion. Okay. Now coming to the load torques. Load torque. What are the main components of load torque? Components of load torque. The various components associated with the load torques are: number one is the friction torque. TA. Okay. Number two, torque required to perform. I'm sorry, that is the final torque. Next is the windage torque. TW. Number three is the torque required to perform useful mechanical work. That is T small l. Okay. Now, if I start with the friction torque, TF. Okay. TF has several parts. That is, number A, torque at standstill. Torque at standstill, which is also called static friction. Also called static friction or stiction. Okay, it is TS. This is the one component of the friction torque. Okay. Next, V is the viscous friction torque. Viscous friction torque, that is TV. which can be equated as, or which is directly proportional to the velocity, that is omega m, or we can write Tv equals to B omega m. B is the viscous friction coefficient. Okay. B is the viscous friction coefficient. Okay. Next, number C is the Coulomb friction torque, which is constant. Coulomb friction torque, that is Tc, which is independent of the omega, that is constant. Okay. Independent of omega. Okay. This all about the friction torque only. This is number 1. Number 2, windage torque. Tw. Windage torque is directly proportional to the angular speed square. That is, windage torque is directly proportional to the omega m square, or Tw can be written as C omega m square. Okay. If I remove the proportional sign, then the constant becomes C. Okay. Now the total load torque we can write TL equals to T small l, that is used to perform the mechanical work, plus B omega m plus Tc plus C omega m square. As the static friction is very small, we can neglect in this expression. Okay. As Ts is very small, can be neglected. Okay. Now come to the graphical representation of the various kind of torques. I am drawing the graph here so that it can be visible at a glance with the expressions. First, friction torque. If I draw, this is the torque, this is the omega m. First is the stiction. Stiction is nothing like this. in the third quadrant like this. Okay, this is the stiction TS. TS is also TS. Okay. Next is the viscous friction. This is the proportional TV. Okay. Next is the Coulomb friction. That is the constant. Coulomb friction. Okay. This is constant. Okay. Now if I draw the equivalent or the total torque, if I draw the total torque, it becomes this is T, this is omega m. It is nothing like this is friction. After that, it is like this. Okay, this is the total friction torque. This is TF.